The next topic is combinations. Suppose we have three distinct objects x, y and z, and using them we want to form groups taking two at a time. In how many ways can we do this? Obviously in these three ways. In this group we have x and y, here we have y and z, and here we have z and x. These are the only possible ways in which you can form the groups taking two at a time out of these three objects. Note that in a group the order in which the elements are considered is immaterial. It's just a group of the two things x and y. Whether you write x first or y first, that does not change the group. However, in permutations, we considered order. Permutation was about arrangements, not simply selecting some objects but arranging them in a particular order. Had we considered permutations of these things, taking two at a time, we would have got these 6 permutations. For this group, we have two ways of ordering its elements, and for the others as well. Now we know how this number 6 comes. This is the number of ways of arranging three objects taking two at a time, and that is 3p2, which turns out to be 6. But we don't want this number. We actually want only the number of ways of selecting two objects from three objects. So that means we are counting twice the number needed. That's why we have to divide by 2. This 2 is, however, what? This 2 is the number of ways of arranging the objects in a single group, which we don't want. That is why here we are dividing by 2. In general, it will be r factorial if in a group there are r objects, so I have written 2 factorial. Now we are going to see more examples of this type so that it becomes clear. Say we have 4 distinct objects A, B, C and D, and we want to form groups using them taking 3 at a time. These 4 groups can be formed. This one has A, B and C, this one has B, C and B, C, D and A, B and D. However, how do we get the number 4? How do we calculate it? We know how to arrange 4 objects taking 3 at a time. The number of permutations we know. From there we have to figure out this number, just like the previous example. The number of ways of permuting or arranging 4 objects taking 3 at a time is 4p3, that we already know. In each such arrangement, if you think of it carefully, actually there is also a selection. First you have to select 3 objects and then you have to arrange them. For example, if your selected objects are A, B and C, then they can be arranged in these 6 ways, which is 3 factorial, the number of ways of arranging 3 distinct objects. But what is our number? The number we need is 4. However, this is much bigger than 4. This turns out to be 24. And this same thing happens for each of the other groups. So that means the number of arranging these things, taking 3 at a time, is 6 times the number that we need. That's why we have to divide this number by 6 in order to get this 4, this number 4. That is, we have to have this 4p3 divided by 3 factorial is 4, which is our number. So our number is revealed to be this type of thing. It comes from that type of formula. Let's test our understanding with another example. This time also we have A, B, C and D, but here we are going to form groups taking 2 at a time. And you can verify it yourself. These are the 6 groups you will have. This one has A and B, then B and C, C and D, D and A, C, BT. So how do we get this number 6? This is how, if whatever we figured out just now is true in general, then this is how the number 6 should come. Does it really come? Let's see. 4p2 because first we count the number of ways of arranging A, B, C and D taking 2 at a time. That is 4p2, and then we have to divide by 2 factorial, the number of ways of arranging 2 objects. So that number is this. So then you apply the formula for 4p2. 4 factorial divided by 4 minus 2 factorial. This 2 factorial in the denominator is just 2. Then 4 minus 2 is 2, so you have another 2 factorial in the denominator, and 4 factorial is 24. 24 divided by 4 is 6. Yes, it's matching. So that means our idea is correct. Any such group is called a combination. For example, this group consisting of A and B is a combination of these 4 objects taking 2 at a time. And the number of combinations is denoted using this notation. In this case, this is 4C2, the number of combinations of 4 objects taking 2 at a time. Just like you have 4P2 where P stands for permutation, C stands for combination. From those examples, we easily get this theorem, whose content is this. The number of permutations of n objects taking r at a time equals the number of combinations of n objects taking r at a time times r factorial, where r, for now r is a positive integer less than or equal to n, and n of course, needless to say, is also a positive integer. In case you suddenly get confused about this relation, this is where it comes from, the thing that we saw just now. NCR equals NPR divided by r factorial. So you multiply both sides by r factorial and you get this. Now there are some observations that you can make from this relation. The first observation is this. You can get a direct formula for NCR without having to write NPR every time. So what you do here, you put the formula for NPR, n factorial divided by n minus r factorial, and then divide that by r factorial. So you get this formula for NCR, n factorial divided by n minus r factorial times r factorial. And the second observation is this. There is only one way of choosing no object from a set of n objects. You don't choose anything. That can happen in only one way. So that's why NC0 should be 1. Just like NP0 is 1, so NC0 is also 1. But what happens if we put r equal to 0 in this formula? Then also, after calculation, you get 1. So that means the formula works even when r is equal to 0. You recall that in the statement of the previous theorem, we kept r greater than 0. But actually for r equal to 0 also, it makes sense. The third observation is about the choice r equal to n, that is NCN. NCN means what? NCN means the number of ways of choosing n objects from a set of n objects. That means choosing everything. That can be done on only one way, and the formula also gives you 1, because you put r equal to n, this becomes 0 factorial, and here you have n factorial. After cancellation, you get 1, because 0 factorial is 1. Next we have number 4. Say r is a non-negative integer less than or equal to n. Non-negative means not negative. But then if something is not negative, either it is 0 or positive. So that means whenever we say non-negative, it means greater than or equal to 0. Then what can we say about n minus r? Because r is less than or equal to n minus r is greater than or equal to 0. And at the same time, because r is greater than or equal to 0, minus r is less than or equal to 0. So adding n to both sides, you get n minus r less than or equal to n. That means if r is like this, then n minus r is also like that. Now what will happen if we take NCN minus r? We can choose here n minus r because it satisfies these inequalities. By using the formula for NCR, we get this. N factorial divided by n minus this lower number factorial times the lower number factorial. This thing, however, is nothing but r. So are you not getting NCR? Yes. Just these two numbers in the denominator have been written in the opposite order. That does not matter because simple multiplication. So NCR is NCN minus r. So there is a symmetry in these numbers, NCR. Next, we have another relation involving these numbers, NCR, which is even more important than this one, this theorem. NCR plus NCR minus 1 equals n plus 1CR, where R satisfies these inequalities. Why do we not write R greater than or equal to 0 here? That is because all these C's have to make sense. What is the condition? The condition is that the lower number should be less than or equal to the upper number and should be non-negative. That means greater than or equal to 0. For these inequalities, NCR is okay. Okay, if R is greater than or equal to 1, obviously it's not negative and it's less than or equal to n. But we want this greater than or equal to 1 so that R minus 1 becomes greater than or equal to 0. That is why. Otherwise, if you just simply take R equal to 0, this becomes meaningless. NC minus 1 has no meaning. What about this one? This one is also okay. If R is greater than or equal to 1, obviously it's greater than or equal to 0, and if it is less than or equal to n, obviously it's also less than or equal to n plus 1. Why are we spending so much time with these numbers? It seems like we derived the formula for NCR and then we forgot about combinations altogether. We started playing with these numbers themselves. That is because you will see these numbers elsewhere also in another chapter. They have a name also. They are called binomial coefficients. The reason for that name will be clear in that chapter only. That chapter is on the binomial theorem. And these numbers are very special. They have many other properties which you will see in different places in mathematics. To prove this, we just take the left hand side, NCR plus NCR minus 1, and then use the formula for combination. NCR is n factorial divided by n minus r factorial times r factorial. Just like that, this one is n factorial divided by n minus, here the lower number is r minus 1. So we put r minus 1 within brackets carefully because there is a minus outside. Factorial times r minus 1 factorial. And we do a little something here in the denominator of the first term. We write in place of this r factorial, r times r minus 1 factorial, keeping the other things as they are. What happens to this one? This one becomes n minus r plus 1 factorial of that. We don't change the other things, but now we will change more. Then in the next step, we keep this term as it is and change the second term. In the second term, we have this in the denominator, n minus r plus 1 factorial. In its place, we write n minus r plus 1 times n minus r factorial, because that's how factorials work. And the other two things we keep as they are. Then you notice that there are common terms. N factorial is present in both the terms of this sum. N minus r factorial is there and r factorial is there. So we can take these things outside. Here we will be left with 1 divided by r, and here we will have 1 divided by n minus r plus 1. And then we do the calculation here, and this is what the numerator becomes, n minus r plus 1 plus r. So you can see that r and minus r will vanish. And that leaves us with n plus 1 in the numerator here. Everything else is same. But then you combine things. You have n plus 1 and n factorial in the numerator. They can be combined to write n plus 1 factorial. In the denominator also you can combine two things. Actually there are 4 things. You combine 2 of them and 2 others. You combine n minus r n minus r factorial and n minus r plus 1. So together they become n minus r plus 1 factorial, but you can write it slightly differently. N plus 1 minus r factorial, same thing, but we do this so that we can recognize what we are getting. Similarly, combining r and r minus 1 factorial, here you have r factorial. So is this not n plus 1 CR? You see, n plus 1 factorial divided by n plus 1 minus r factorial times r factorial. That's why instead of writing n minus r plus 1, we wrote n plus 1 minus r. So So here the proof ends. And then we turn to word problems. We have an example here. A committee of 3 persons is to be formed from a group of 2 men and 3 women. In how many ways can this be done? That's one thing. And then we also have to find how many of these will consist of 1 man and 2 women. In total there are 5 persons and your committee should consist of 3 persons. So that's why the first answer is 5C3. It's just that. And the second one is what? In how many of these committees do we have 1 man and 2 women? There are 2 men, from which you can choose 1 man in 2C1 ways, and from 3 women you can choose 2 in 3C2 ways. Why do you have to multiply these numbers? That is because unless you take all of these things into account simultaneously, the full committee is not formed, and these numbers influence each other. They together influence the total number of such committees. That's why you are multiplying. Only this 1 or only this 2, they do not by themselves form the committee. They have to come together. That is why we are multiplying. Otherwise, we would have added. So that's the answer. There is one more example. What is the number of ways of choosing 4 cards from a pack of 52 cards? A standard pack of 52 playing cards. And obviously that number is 52C4. There is more to this example. The next part asks this: in how many of these choices the 4 cards are of the same suit? In a standard pack of 52 playing cards, there are 4 suits which you already know, where the symbols look like this. I do not have red ink. Okay, you may already know that these 2 are red. You may know means obviously you know. Now we have to choose the cards in such a way that they come from the same suit. So for this one, if all the cards belong to this suit, then they can be chosen in 13C4 ways, because each suit has 13 cards. 4 times 13 is 52. The same can be said about the other types of choices. Say if all the cards if all of them are hearts, then that also can be done in 13C4 ways. Why are we adding the numbers here and not multiplying? That is because you have already made the choices. Here each combination already has the 4 cards. We don't have to combine these 4 cards with more cards. Okay, that's why this is a complete number, this is another complete number. That's why we are adding. This is the total number of such choices. Next, part 2. In how many of these the 4 cards belong to different suits? All of them. Because we have to choose the 4 cards from different suits, and there are 4 suits, so 1 card has to be chosen from each suit. From a suit, a card can be chosen in this many ways. 13C1, because there are 13 cards in a given suit. The same with the others. Do you see the difference here? Here we have to multiply, because these 4 ones together will come and make a single choice of the 4 cards. That is why instead of adding, here we are multiplying. Part 3 next. In how many of these the 4 cards are face cards? There are 3 face cards in each suit: King, Queen and Jack. So in total there are 12 such cards, and from them only you have to choose these 4. So that's why this time we have 12C4. Next, part 4. Now in each of our choices we need 2 red cards and 2 black cards. There are 26 red cards and 26 black cards. So the number will be 26C2 times 26C2. And again we are multiplying because we need them to come together to form one single choice. And finally we have part 5, where we need in each of our choices that all the cards be of the same color. There are 26 red cards, so if all our chosen cards are red, then that can be done in 26C4 ways. Similarly, for the blacks also we will get 26C4. and we have to add here because this 4 is not incomplete, like those 2 and 2 are the 4 ones, that is why we are adding.